Okay, so this week's subject is numerical integration. How do we move this thing down? PC. Oh wow. He's been teaching before. Okay, so today, on Monday, we covered the Newton code rules, which are trapezoidal rule, Simpson's rule, and their composite implementation. And why? Because we have many mathematical functions which we cannot analytically integrate. We cannot find an antiderivative for the original function. That is reason one. Reason two is that you simply might be provided with a set of discrete x versus y data. So someone gives you an Excel data sheet or a text file with x versus y and then asks you to integrate the area under the function. So we covered trapezoidal rule and Simpson's rule. Okay. Now those methods are rather old. In other words, they've been out there for many years. And if you use the composite variant and you do have the function and you make the panels really small, you actually will do a reasonable job. But that means you use a lot of panels. That means you need to use a lot of x values. And a computer scientist then says that is computationally not very efficient, because I like to get the same result within the least amount of calculation time. So that's why another method has been introduced, and that's called Gaussian Quadrature. Okay, and that's the topic that we'll talk about today. And Gauss-legendre quadrature, and they're essentially the same. So don't get confused. So Gaussian quadrature or Gauss-legendre quadrature are the same. So don't get confused. I will typically refer to Gaussian quadrature if there's a question on the exam or on the quiz. Those methods have nodes, this should be number 3, and weights, and we'll also talk about their composite implementation. Any of these rules, like the trapezoidal rule, Simpson's rule, you can also implement compositely, which means you solve panel by panel instead of directly the entire integral. You just solve sub-intervals so that they become more reliable. Now yeah, the last lecture on Friday I'll cover the last 20 pages. Now, so you know, like we always start with clearing the screen, and I clear everything, clear it all, and then I start on top. Or clear the memory and then I'll start here on top. Now, we already went over this previously. What is integration? This function fx is x. We can derive a primitive function for this, an antiderivative, which would be an half x squared. And then we can integrate this function between any two x values. So that's an obvious example. But what if you do not have a function? You just have a set of data. Or your function is so complex that you cannot derive a primitive function. Yeah? Then you need an alternative method to integrate. And that's numerical integration can help you with this. Now, we went over all this previously, so I'll just do all this quickly. This is the example of the function x times exponent minus x. This is how the function looks like. And now we like to integrate this function. Yeah, that was the central idea. Now, so we have solved we have talked about trapezoidal's rule. We actually solved it in the code analytically, and we implemented, and the composite rule. And we talked about Simpson's rule and the composite implementation. Okay, so we're good so far. But both methods still require, even though Simpson's rule is way more efficient than the trapezoidal rule, both methods still require a relatively large number of x values at which you have to compute the f value if you can. In case of discrete data you cannot, and you're stuck with the x data you have, and the panel width can vary, for which you have the numerical solution. But people were not happy with that. They were like, okay, I think we can do this better. And that's where the method of Gaussian Quadrature came in. Okay? Now, the theory of this method might be difficult to follow. Okay, so if you go to the Wikipedia page, you type in Gaussian Quadrature in Google, you'll find the Wikipedia page immediately, and it will explain to you what Gaussian Quadrature is. Might give you a little bit more insight. But essentially, it solves the same thing as we've done previously with the trapezoidal rule and with Simpson's rule. But in both those methods, we selected the x values at which we like to compute the function values. We stated what's the lower bound of the integral. We stated what's the upper bound of the integral. And then we specified how many panels we like. And by definition, if you specify the number of panels and assume they have a constant width, then you know each next x value. So you have all the individual x values that you like to use to solve numerically the integral. Gaussian Quadrature doesn't work that way. Gaussian Quadrature picks the x values for you. Okay? So, and it picks it in such a way that the resulting estimate of the integral has the least or the smallest possible numerical error. And there's a whole theory underlying this, and the author attempts to talk about this in the book. And I don't expect you to understand that, but essentially what we have left is this thing here, where I is the integral between a and b of a Lagrange polynomial f1 times L1 plus f2 times L2 plus f3 times L3 all the way plus fn. So f is the function value, fn is the function value at my last x data point times ln x. Now you can rewrite this thing where you use coefficients. It's coefficient 1 times f1 plus coefficient 2 times f2 plus coefficient 3 times f3 all the way up to coefficient n times fn. Now, and that is equal to the sum from I is 1 to n of the coefficient times its function value, where the coefficient is equal to the integral between a and b of your basis function. That's the underlying idea. Now it's all very abstract. You're like, oh, what the heck is going on here? I understand. So we can go to Wikipedia if or we don't really have to, but so here I have a link. Go to that link, okay? So Gaussian Quadrature picks the x values for you and says if you have this integral, then these are the x values you're supposed to use, and these are their associated weights. Because what you see here in the function, you have C1 times F1. Okay? So C1 are the weights, and F1 are the corresponding function values to our x values. So Gaussian Quadrature, let's say that you say I want two values, I want to use two x values, then Gaussian Quadrature will give you two x values, x1 and x2. Of each of those two x values, you know what their weight is. In this case, that's C1 and C2. So C1 is the weight of x1, C2 is the weight of x2. And F1 is the function value corresponding to x1 and F2 is the function value corresponding to x2. And it goes too far here to go over all this theory. We just don't have the time. Okay? But if you read the Wikipedia, it will get a little clearer. The only thing is that Gaussian quadrature assumes that any integral that you're trying to resolve resides in the interval between -1 and 1. In that interval, Gaussian quadrature will tell you what are the optimum locations to pick the x values. But in reality, we like to solve integrals that are between 5 and 10, -20 to 27. So how do we apply that method then to integrals that are not between -1 and 1? Now that's simply a linear scaling. Okay? So an example here. We go back to our error function here. And our error function is something that is 1 over the or 2 over the square root of pi or so times the exponent minus x squared. And now we like to integrate this function between x is 0 and x is 1. Okay? So how do we apply Gaussian quadrature? Because our interval is between 0 and 1, and Gaussian quadrature only is between -1 and 1. So let me, to make one thing clear, there's built-in scripts that will tell you which x values to use and their corresponding weights. So if we go back to our equation here, that's CI. So we have built-in functions that you specify, I want to use 8 x values. Then that function spits out the 8 x values between -1 and 1 that you need to use and their corresponding weight. So you already have this. You know that n is 8. You know for each x value what its weight is. But the only thing you then need to do is evaluate the function value at each x value. And if your interval is not between -1 and 1, you need to scale those x value that function gives you linearly to the domain that you're interested in. So I trust that you read all this at home, yeah? That's happened. So let me give an example here, okay? So this is the definition of a Gaussian quadrature rule, where the integral is b minus a divided by 2 times the function value of c times b minus a divided by 2 plus a plus b divided by 2 and dc. And that's the solution. Okay? Now, if you work that out, what you're going to get is something like, is approximately b minus a, where b is the upper bound of your interval that you're trying to resolve. So that doesn't need to be 1, that can be 10. And a is, let's say, -100. Times the sum over the number of x values you have, n is the number of x values you have, of the weight of a particular x value times the function value at Ci is derived from that Gaussian quadrature function. Those are the optimum locations. And this here, what you see here, is the scaling of that C value that's within the range between -1 and 1 to the range between A and B that you're interested in. Because Gaussian quadrature assumes that you solve an integral between -1 and 1, and maybe you solve one between -10 and 10. So it will get clear, I think, in a little bit, and that is that if we select that with Gaussian quadrature that we only like to use 2 nodes, so 2 x values to solve numerically for the integral of a function, then the optimum locations of the x values are minus 1 over the square root of 3 and 1 over the square root of 3. And why that is, don't worry about it. We will always supply the script with it if we're going to use it. Okay? These are just the optimum locations. So instead of saying, you know, I want to solve an integral between minus 1 and 1, I just pick minus 1, 0 and 1. Because I use two n values. Or if I use three n values. If I use two n values, I just pick minus 0.5 and 0.5 or so. No, there's a whole theory behind this and states that if you want to solve an integral between minus 1 and 1, then if you use two nodes, two x values, because you like to use the least amount of x values, then the optimum location of the first x value is minus 1 over the square root of 3. And the second x value is 1 over the square root of 3. So it's actually symmetric. Yeah, because the first one is negative, the second one is positive. Now, from my x values, I need to go to what's called my c values. Why? Because oftentimes my x values are in the domain between minus 1 and 1. The code that I wrote, or is written, picks the x values assuming the integral is between minus 1 and 1. But what if it's between minus 10 and 10? So that's what happens over here, where you have a linear scaling, where you scale the values that you got, the optimum values, but now you scale them to the interval, the integral interval that you like to resolve. And b is the upper bound, a is the lower bound. So in our case, b could be 10, a minus 10. So you linearly scale. Now, once you have those c values, then you can actually evaluate those function values. Okay? Now, what we know, that if we only use two nodes, if we only use two x values in the domain between minus 1 and 1, but then linearly scale to the domain that you're interested in, that actually the weight, the c in front of our f, yeah, in front of our equation is 1. Both of them have a weight of 1. That we know. So now the integral becomes 0.7466. But we need to multiply that because the error function is 2 over the square root times exponent minus x squared. And what you see here, the only thing that I did here is exponent minus x squared, where you see these additional terms that reflect the multiplication going from x to the domain that we're interested in. Yeah? So now what you see is that if I multiply my integral with that 2 over the square root, you get 0.8427. And if I numerically resolve the error function, then the integral between 0 and 1 is 0.8427. Which means I'm getting an estimate of 0.8424. So with only two nodes, I get an estimate that is really close to the true value of the error function. And the error function is highly nonlinear. Okay? So, again, to summarize, Gaussian quadrature does not, like previous methods, take in certain x values that you specify. Instead, it assumes on an interval between minus 1 and 1, it picks the optimum location of the x values that you should use. For each x value, it also knows its corresponding weight in the calculation of the integral. And so that's what you see over here. Essentially what you have left is this, is the sum of I is 1 to n, and n is the number of x values, of ci. Ci is the weight. So the weight of measure of xi times the function value at xi. So it's a really relatively easy method. The only thing you need to specify, how many nodes, how many n values do I, what's the size of n? But that's on an interval between -1 and 1 they're optimally picked. If you have an interval that ranges between 0 and 10, 10 and 100 as an integral, you need to linearly scale those x values to that appropriate interval, because this is picked on an interval between -1 and 1, so you linearly scale them. And you can do that with a rule like this, where this is the optimum value and you multiply that with the difference of the upper minus the lower bound divided by 2 plus the lower plus the upper bound divided by 2. This is the rule. Okay? And then you know where in your original function which values you should use. They're no longer between -1 and 1 unless your integral is between -1 and 1. So to apply Gaussian quadrature, you need to transform each integral to one that lies between 0 and 1. Now, you do that by a simple transformation, where you first derive the optimum location of the x values and their weights, because the integral is the weight times the function value at those optimal x values. So, if we know the optimum x values and their weights, then before we run the optimum x values through our function script so that we know the y values, we linearly transform them to the appropriate interval that we're resolving. Because most integrals are not between -1 and 1, they could be between anything. So the author wrote a table, this one, that gives us, for a number of different cases, smaller than 8, gives us the optimum location of the x values, again assuming that the integral is between -1 and 1. So if I only use one x value, the optimum choice is take your x value in the middle of the domain. X is 0. The associated weight of that is 2, and that's c, remember? So we get now 2 times the function value at x is 0. That's our estimate then of the integral between whatever. If we use 2 nodes, then we have x1 is -1 over the square root of 3 and x2 is minus x1. So that's 1 over the square root of 3, and both have a weight of 1. Now if you use, the more nodes you use, the closer your integral to reality. So here you see all the different results with the location of the x values, and there is a corresponding weight. So let's look at the first case, okay? Because x is 0. So it states that if we only use one x value to numerically integrate, we should take, because we are between -1 and 1, we should take the middle of the domain. Now let's see if that makes sense. If we go back to our equation here, so let's say that b is 100, a is 0. Yeah? Then what we get, x1 was 0, that was our optimum location, but in view of -1 and 1. But no, we work between 0 and 100. So what we get is that the transformed x value is called c is 0, because 0 was the optimum choice between -1 and 1, times b, and that was 100, minus a was 0. Now, divided by 2, so 0 times something is 0, plus a plus b, that is 0 plus 100, that's 100, divided by 2 is 50. So, if we have an integral between 0 and 100, then the optimum location is 50. Does that make sense? Yeah, because that's in the middle of the interval between 0 and 100. So and x1 is 0 is indeed in the middle between x is minus 1 and x is 1. So Gaussian quadrature always assumes an interval between minus 1 and 1. The only thing we need to do is linearly transform those x values to the domain that we're interested in. Okay, so so we've done this and we got an answer of 0.8424 and the true answer was 0.8427. So I can approximate the error function that in the previous lecture with trapezoidal rule we needed many x values. I can get a really good answer with just 2 x values. The difference is really small. So that's pretty good, yeah? So it makes it more efficient. Now the author also wrote a more general code where he said, you know what, this script, this table thing is restricted to 8 different x values between minus 1 and 1. And what if you want to use 10 or 100? So he wrote a more general script that's called edit gl node wt.m, and here you can specify any value of n, so you can specify any number of x values you like to use in the domain between minus 1 and 1. And what you're going to get out are the optimum location of x, that's the first output argument here, and the corresponding weight of each x value. So if we go back to our main script, you see that if we use 2 nodes, we knew that the weights were 1 for both of them, and this is minus 1 over the square root of 3, and that's 1 over the square root of 3. But we can also use 10 nodes between minus 1 and 1. So what you now need to do, because your integral might not be between minus 1 and 1, but between 0 and 10, you linearly scale each of those values in the domain to 0 to 10. And we know the rule. Okay, so this is the rule here, where the scaled value of the optimum x value, so Ci, that's scaled, is xi, which we know that just came rolling out of our function, times b is the upper value of the integral you're trying to resolve, a is the lower bound, divided by 2 plus a plus b divided by 2. Now let's see if this makes sense. Yeah, because now if we define this to be xi, then you can have an idea what's happening. So now I have my xi values. This is between minus 1 and 1. Now imagine now that I say that a is 0, b is 10. Yeah? And let's see how this plays out. Oh, if I scale... what is not valid here? Oh. So this is, if I now do xi, ci, oh. You see, this was originally between minus 1 and 1, and here I scaled it between 0 and 10. Once I scaled it, so once I have the right hand side column, I can run that and calculate the function value at each x value. If I calculate the function value of each xi value or each ci value, then these are the weights associated with each value. So I just do this times the function value at this value. I do plus this times the function value at this value, plus this times the function value at this value. Now that's how Gaussian quadrature essentially works. That's all to it. Okay? So here, another example, I use 6 nodes. This is with 6. If I use 6 nodes, these are the optimum locations. You always see they're symmetric. So this one is minus that one. This one is minus that one. This one is minus that one. Okay? And always use an even number of nodes. Okay? That makes things easier. Now, again, if I define A is 5, and now calculate C, what you have is x and C. Oh. X and C. And here you see this was originally, according to our script, the optimum location of X if the integral were between -1 and 1. And this is the corresponding value because our integral, unfortunately, is between A is 5 and B is 10. So this is just a linear scaling that you can accomplish with this simple rule. You just linearly scale this value to a range that's different. That's no longer -5, 5, but that's 5, 10. You can do that with a simple line like this. And the dot is used here so that I can work with factors of X. Now, let's now we have our C values. Now let's come up with a simple example here. Okay, so let's consider this example here that our original function is 2 times x squared. Yeah? Now I have and I want to integrate this between 5 and 10. Yeah? So now I have my C values that I just derived. So now what I do, I calculate the function values because my function script was 2 times x squared, but x are now my optimum locations, which are called C. So now I have my C, I have my F. So this is my original x values. Then I have my C values, I have my F and C. So these are my original x values according to Gaussian Quadrature. These are their scaled values. These are the function values according to my function. So this is the function value at 9.8312. And these were the weights. And again, this one and this one is computed by a script. Okay? You don't need to know how to do that. Now we can simply fill out our rule, which is this sum, which is the sum of the product times b minus a divided by 2. Okay, I left that out previously, but this is the integral. This is a reduction, or is a scalar that you need to multiply with. Okay. So this is our estimate of the integral of the function 2 times x squared, yeah, of this function is the result of 583,333. And sometimes, as you notice when you look in your script, there's some edits, some small things that I changed while going over it, okay? But no big deal. Now, fortunately, this function we can analytically integrate, yeah? The answer is 2/3 times x to the power 3. So we can calculate what the actual integral is. And what you see, you get the exact same result. So this is the analytical estimate. This is the estimate there according to I underscored a GQ means Gaussian Quadrature. You see, you're going to get the same answer with only 6 nodes. And you can see that further here, that the difference is really small. It's smaller than 1e minus 12. Now, you can also, the last thing for today, give me please a few more minutes, is the composite implementation. Like, if you want to integrate something between 0 and 10, you do not have to derive directly the x values for the entire domain. So you're going to get the x values between -1 and 1, and then you linearly scale them between 0 and 10. You don't have to do that. You can do a composite implementation. So you divide the function in different panels, like a trapezoidal rule, for instance. Yeah? Now, this is the recipe, and this is the numerical implementation. So I define that I want to use 5 panels, that my lower bound is 0 of the integral, my upper bound is 1. So then I have n is 4 nodes. Based on this number of nodes, I define this function GL node WT. You don't need to know, okay? So that gives us, for a given number of nodes, the optimum location x underscore opt of the x values and their associated weights. So now we know the optimum location of x. We need to scale that back between 0 and 1, because we like to resolve between 0 and 1, whereas the optimal location of x with Gaussian Quadrature assumes an integral of -1 to 1. Now we calculate h, and essentially what you're doing here is you just move from panel to panel, you apply the same nodes, calculate the integral for each panel, and now what you see here is the result you're getting. I can send this updated script here, where you see that the total integral here, IQQ, is 0.8427. So if I solve the error function with 5 panels, now I'm going to get something that is very close to the original. It's almost identical. Okay? So I only use 4 nodes, n is 4. In each subinterval I use 4 x values, but I use 5 panels here, n is 5. So I divide my interval in 5 different panels. And as one last thing that I like to highlight is that there's a demo here that I like to, that there's a function here that the author wrote that does Gaussian Quadrature for you. That's this function that just does everything we just talked about, okay? And you can actually, if we can exercise that function here for the same example where we specify this is our error function, that's 2 over the square root of pi times exponent minus x squared. That's the one we try to integrate between 0 and 2. We use 5 panels for this, and we use 4 nodes in each panel. Okay? Now this function can then derive that it says that the integral is 0.9953. What is now the true answer? That's 0.9953. This is the true integral because it's an error function, so you can directly calculate the integral. And this is the difference, so it's really small. And then he wrote a really nice demo where we show here, we compare here, as last thing here, I hope this all fits on one screen. You see here, this is Gaussian Quadrature. The top one is Gaussian Quadrature with 1 panel. But you increase the number of nodes in that panel. Okay, so that means you use 1 panel between the lower and the upper bound, but you just increase the number of nodes. So you see that you already do pretty well with only 4 nodes. Okay, this is for the error function. Then the second one is where we actually use 3 nodes, but we change the number of panels. Okay, so what you see that if you use 3 nodes, and you use 4 panels, and you're going to get very acceptable result. In summary, Gaussian Quadrature, instead of you defining which x values you use, and then running the function value for that, or computing the function value, Gaussian Quadrature tells you which x values to use for any function. And that's a script. You do not need to know what the x values are if you use 12 nodes or so. That's a script we will always provide. So that script will give you the optimum x values between -1 and 1 and the associated weights. Then you need to scale those optimum x values between -1 and 1 to the interval that you are interested in. Okay? Then you compute the function value at those values. And then you just fill out the equation, which is b minus a divided by 2 times the sum of each coefficient times its corresponding function value. And you're going to get really good result because remember, last time we needed like 200 x values to solve a problem like this. Now we can only use like 4 x values. So a tremendous increase in numerical efficiency. On Friday we will talk further about the project. Okay? The final project. We will have 10-15 minutes. I'll give some more hints, introduction and all that. All the information should be in the Word document. You can always Google a little bit. We will have 10 more pages to go of this chapter, okay? And that will cover the built-in functions. That will go over the stuff we already went over, but then by writing it ourselves. So good luck.